Hello, everybody. Good morning, good evening, good afternoon, and thank you for joining this Neo4j live 2 weeks after
Hello.
Node. So I hope you all recovered from 24 hours of Neo4j presentation on beginning of November. But now we're back with our sort of regular schedule with live streams on the channel. So happy to have you all back here today. We had a funny conversation already in chat earlier while the video was running about Graph 8, which I need to check out. Nico posted that in chat, so I need to check that out. So people having a good time here, and saying hello from Pune, from Paris, from New York, from Manchester, from Lima, from India. So on LinkedIn. So great to see you all join today, and yeah, welcome everybody. I'm happy to have Yoan Sallami join me today. On HybridAGI, graph-powered self-programmable AI. So that's going to be our topic for the session today. Hi, Yoan. How is it going? How are you doing today?
Hello. Hello everybody. I'm doing great. To present myself, I'm a PhD in AI and robotics. I've been working before in humanoid robotics, and social robotics, which are quite a difficult topic in robotics. One of the hardest domain actually. Um, I was working with humanoid robots, and when all the LLM crazy became started, I started to implement a system based on my knowledge on making a robotics system. So I will share my screen just a bit.
Cool. Yeah.
Okay.
Let me see when I get your screen, then I can switch over here. Here it comes. Right. That works.
That works?
Yep.
Okay. So the company that we started is called Synalinks, and
Maybe Yoan, sorry for interrupting. Maybe you wanna get rid of this little box that says you're sharing your screen. Maybe yeah, or you can click on the little that. Yes, exactly.
Okay.
Yeah, then it goes away.
Thank you.
Cool.
When all the LLM craziness started, we started a company that is called Synalinks, and the main idea behind it was to promote a neuro-symbolic system. So here is our team, and when we started the company, our idea was really to push neuro-symbolic systems. To push those neuro-symbolic system, because in robotics we use these kind of systems a lot. So here is some of my previous work that I've done with humanoid robots, as I said previously, and it was about creating a graph structure for explaining the scene. So you have different kind of objects, you have maybe people in the scene, and you want to describe the scene as a graph. And that graph goes into an ontology system, and based on that, the robot is able to interact with the people and ground information and entity in the real world. So actually, my work was about many different things, but mostly about combining the robot perceptions and simulation engine to make the robot able to infer the position of the objects even when they are occluded by the camera. And also about theory of mind. So theory of mind in robotics, we use a lot the graphs, but we don't only infer a graph for the robot, but we also infer a graph for the humans. And the way we construct it is that we have the graph from the robot, and we filter some part of the graph. And how we do that? We do that using what we call visual perspective taking. So we take a picture from the point of view of the user, and from that we are able to compute the visibility of the objects. And based on that, we can filter the main knowledge graph and create other knowledge graph for the people that the robot is interacting with. So when we started HybridAGI, the goal was really to to give you a bit of history. The system is now 1 year old, and we started at the very beginning of the agents, the LLM-based agents, and we had kind of a frustration about agents. They were going into infinite loops. Sometimes the TLDR is that they was not reliable. And so the idea behind HybridAGI is to use concepts from computer science, but also from cognitive science to create a system that is able to work reliably. And so we do that by controlling the agent system from end to end using a graph. So there is no React agent in our system. I mean, you can implement a React algorithms, I would say, but that's not the point of the system. The system is really made to be able to program more complex agents than the React one that didn't give us really reliable results. So we do that by managing the knowledge using graph databases. And we picked the Cypher language. We picked the Cypher language because it's really easy to learn and easy to read for humans. So our hypothesis was that if we have a language that is easy to learn for humans, it could be easier to learn for LLMs, because as LLMs are really a proxy of our natural language. And if we have a language that incorporates a lot of natural language, we could create an intermediate language between the goal of the user and the execution of the system. So basically, it's really a memory-centric system. We have different kind of memory, and we can use them all at once if we want in the same agent. We are not limited by the number of tools that the agents can use, simply because as the system doesn't really choose the tool that it have to apply, because they are specified in the programs. So the way that it works is that each time it needs a program, the prompt is constructed in a way that it gives only the information that it needs for these particular programs. This particular tool, sorry, and so we are able to accommodate an infinite number of tools as long as you describe the whole logic into a graph. So there is different memory that we implemented. So the program memory is actually it's a dependency graph. We see here, we see this memory here, and it's a dependency graph. Why a dependency graph? Because in our system, we decided to really create a kind of a software written in Cypher. That was the innovation behind our system. So you can describe the whole software, and as a software, you start with the main program. So you have the main program, which is the entry point of the agent, and it will interpret the program. So the interpreter is very like a Python interpreter. So in Python, for example, an interpreter is going to interpret line by line and going to execute the given execution. In our system, the interpreter will navigate inside the graph and will execute node by node the graph programs. And that's really key to understand. I would say, like, it's really, if you come from computer science, you already know what is an interpreter. You already know the differences between a compiled language and an interpreter. For example, our system is very different from LangGraph, for example, because LangGraph use finite state machines. The thing with finite state machines is that you define them, and then they are fixed, they are static. Okay, and there is no really a way to modify this state machine on the fly. The only way to do that is to create an intermediate language that the LLM can read and modify. So here it's what we've done with the Cypher language. We have also the memory, the memory, document memory, which is now a classic in RAG system. I won't talk too much about that. It's really a classic now.
Yeah.
The fact memory. So if you hear in this Neo4j stream, you already, I think you already know what is a graph RAG. And the fact memory is the system that stores the triplet. So a triplet is the subject, verb, object, and it's basically your determinist fact that you work with. And we have finally the trace memory. So the trace memory, it's a bit special. It's kind of the episodic memory of the system, but we didn't want to bring too much concepts from cognitive science. So the idea was to really use the concept from cognitive science, but ground every concept into computer science, because it's easier for people with programming knowledge to understand it, and it also it's avoid many pitfalls that people have when they try to mimic too much the human cognitive processes.
Mm-hmm.
So the trace memory, what it does is we basically record each action that the program was performing. So actually what you have is that in this memory, you have the trace of the program that were already executed. As I said, like each memory can be used multiple times and all at once in the same agent, because they have special tools that we can use within the agents to access them, to read-write. So the agent have read-write access to most of the memory system. About the repository, so we currently have it started to get quite famous, and we are really happy about that. So
no, it's good. Great.
Yeah, today we had a really, I would say, like some stars shine more than others, and today we had the 1 star from François Chollet, which is the creator of Keras and the HybridAGI benchmark. And actually, we used some of his work with Keras to come up with an abstraction that was easy for people to understand and to leverage. So actually, that was really quite something for us. And so yeah, here is the link. See if you want to go and check and have a start to the repository. Next,
I put the link to the GitHub repo also in chat.
Okay, thanks. So now we are going to dive into some notebooks. So I will show you really, I would say, basic notebooks. So it will be a graph RAG, so you can get a sense of how to use the library. And then we are going to switch to a more experimental, I would say, feature, which is a copilot for our system.
Cool.
Okay.
Oh, and so, if anybody's watching and have any questions, any comments, then please feel free to use chat and let us know. There was already a question on your slides, if they would be available afterwards. So maybe we can share them with the audience later. But the recording, definitely, this will all be recorded, and you can watch it afterwards anytime in our YouTube channel.
Yeah. So knowledge graph RAGs are nowadays, like, I would say, common. But when we started HybridAGI, for I don't know the reason, last year, nobody was giving attention to graphs because everybody was focused on vector-only RAGs and React agents. And coming from robotics, that was really something weird for us, because graphs are really powerful and they can model almost anything. So actually, they are really useful in many cases and many applications. So here in this notebook, we are going to build a graph that is about basically a movie recommendation system. It's kind of a toy example, but it's show well how the system works. So we have here our input data, and we are going to build the facts that we are going to need in our system. So here it is. We have the facts that we are going to use. So basically, it's just the fact is a triplet that we have.
So here we are. So here we just like create the facts from for the fact memory. So the fact, as I said, are actually triplets. And then we create a graph from them. As you can see, like the nodes are not connected with each other, which is it's a classic problem in graph database. It means that there is duplicate nodes. And actually, we can create a pipeline. So in HybridAGI, there is a really handy way to create a pipeline for data processing. And it's really look like Keras or Hugging Face library. In fact, we took inspiration from them. So it's actually quite normal that the system look like Keras or Hugging Face. So we can create, we can stack modules with each other, and we can create data processing pipeline. So here in this pipeline, we duplicate the entities and we embed the entities and the facts. And by doing that, we can create a knowledge graph. And based on this knowledge graph, we can infer some things, and in this case, we can recommend movies for the users. So here is the part that in HybridAGI. So the thing is, we create a graph program, and this graph program is actually done in Cypher, but we created a way to create them using Python, because when we started our system 1 year ago, the only thing that we did is that we had like the software written in Cypher, and this many people complained about because they didn't know Cypher, or it was too complicated for them. So we took inspiration from Keras, and we created like an intermediary language on top of the DSL to be able to create the programs in Python. So the program can have 4 different nodes. It can have control nodes, which are used for the start and the end of the program. It can have action nodes, which describe the use of the tool for the agents. We can have decision nodes. So the decision nodes are used for the system to branch over the graph based on a question that the developer asks for the system. And actually, the question, the good way to see that is not about really asking question to an LLM, because the LLMs are quite limited, and they really cannot say that they understand what the prompt or whatever. But actually, they are quite good to do some one-shot classification in a one-shot setting. So you have to see the decision of the system as a classification task. So the goal of the decision is to classify the context, and based on that classification, the system will branch over the graph to execute the action of the branch. So and also the last node that is possible to have in our program are the program nodes. So the program nodes are actually like a subprogram in a programming language. So the interpreter have a stack, like in any, I would say, proper interpreter, and you can call other subprograms. And by doing so, you can call subprograms, subroutines, and you can go back to when the routine ends, you can go back to the program that called that routine. So it really looks like a programming language, in fact, for LLMs. And if you create your program, and at the end, what you got is a program that is expressed in Cypher. Okay, and this program, due to the fact that this program is really use a lot of natural language, the LLM is able to understand it quite easily.
And it says here tool fact search, because Paul also has the question in chat. Is that a tool you built yourself, or is that what is fact search?
So the fact search is when you search for facts in the fact memory.
I see. Okay, the one you showed earlier in the slides. Mm-hmm.
Yeah.
Yeah. Okay.
Yeah, exactly. Here. So actually, it is going to look for triplets inside the knowledge graph.
Mm-hmm. Okay, I see.
We have a way to. What is really different from our system from long graph is that because we have. I can also show you this notebook. Because the here. Okay. So this is another notebook, and it's show because actually the programs are embeddable, and what it means is that you can have many subroutines. Like imagine you have like millions of graphs, and each graph is actually a skill for the agents. Okay, and so it's impossible to have in the main program to create a program to like have the good condition to call the right program, etc. Because at some point, if you have a growing library of programs, or you have a program, an agent that is really general and and that have a lot of different skills, you need a way to search for the right skill to apply. Okay, and this can be done because we use the description. So here is the description of the program, but we use the description of all the subroutines to create an embedding for the program. And by doing so, the system is able to search inside its own program library, and is able to dynamically call a program when needed. Okay. So here we create different programs. So for example, this is the one that look like a rag basically, and we have another one that is about telling a joke, for example. So we create a pipeline to embed each programs. So we embed the graph programs that we created earlier, and based on that we create a dependency graph. Okay. So here we have the dependency graph. In this example, it's quite simple, but there is no limit on the complexity of the dependency graph, obviously. And what we noticed when we was experimenting with self-programming agents, because remember the goal of HybridAGI is to have like a system that is able to program itself and to evolve, and I would say like learn new skill on the go. That's really the main goal of the system. And when we started to experiment with that, we noticed that sometimes the LLM wanted to modify its own main program, which is, if you think about it, it's quite not good. And we came up with a system to be able to protect some program. So in programming language, we have some scope. For example, in Golang, for example, you have in C++, you have the scope of some program have a scope, so it can be public, protected, etc. And here we have we made a kind of a scope for the graph programs by only allowing the system to call programs that were disjoint from the main program. Okay, because when you create for example, when you create I would say a learning program, so you will create a program, a main program that says, okay, look for a skill, okay, to perform the user query. If that skill is not present in the database, so we are going to learn a new skill. So we are going to create a plan, convert this plan into a graph program, okay, and we are going to save this into memory. And this is basically a learning algorithm that you can have. And your learning algorithm is in your main program, but you don't want the system, the AI system, to be able to modify this learning algorithm, because it will mess up with all your architecture. So we have to come up with a way to protect some of these programs. And also, it's really interesting in the sense that we can implement some guardrails in the system by, for example, if you want to, I don't advise to have only this guardrail for a system based on LLM, because there is a lot of problems that can arise, like prompt injection, etc. But it's useful to have, like, I would say, a first decision when you receive a query from the user, that will be like checking that the user query is about X topic, this topic, the topic of the system, okay, or check that what the user asked is not against some ethical rules or some safety guards, okay. And what you will do is, instead of calling the subroutine that's going to execute the user query, you shunt your system, okay. So this is really useful to have in a system, and that's why we implemented this safety mechanism to the program. So, for example, here, we have the query of the input query of the user. Okay, it calls the fulfill objective subroutines, and this subroutines is going to find into the memory system, the program memory, other programs to call. Okay, it's going to search them, and then we are going to ask are they relevant or not, etc. And if they are relevant, we are going to use a tool that is called call graph program, that based on the name of the program will actually call dynamically a program. Okay. So basically here it's what happens. So the system is calling the tell joke program, okay, that was searched previously here, and it's going to execute it. So it's able to execute the program, okay. So here is the execution of the program, and then it ends the execution of the program and ends the main program, okay.
Are you guiding this a little bit by this question from Don in chat? Are you using weighted path concepts to help the system make decisions, or how is are you helping the LLM a little bit, or giving it a little bit of a structure for it to come up with
yeah. To help the LLMs to make the right decision, we actually use a chain of thought concept. So if we look at prompting here, I have a notebook that explains the underlying prompt that we use exactly. So when we are making a decision, okay, in context, okay, decision-making steps. So here we have a program that have a decision-making steps, and we create the program. So as usual, And when the system is actually performing the query, we have this reasoning. And this reasoning actually comes from the SPI, because our system is built on top of the SPI, and the SPI have a way to easily create some chain of thought reasoners. And so the goal is to, for example, in this case, it's going to create reasoning steps, I would say. Reasoning, it's not real reasoning, but you know what I mean. And it's going to help the system to perform better pattern matching by let it think before answering. And by doing that, the system is able to have a pretty good decision making systems. About the decisions, there are a few ways to enhance them. One way is to actually ask something that is really grounded in the information that the system has in the prompt. Because when you ask the LLM about a question that requires its internal knowledge, there is a higher chance that it's going to miss the point. When you ask the system a question about something it has in its context, you can see it as like a regex, for example. Let's say you have a question that is going to be, so I retrieve some documents based on the similarity metric, so like a RAG, and you're going to ask, is that relevant? Is your context relevant? Is the list that you fetched empty? If it's empty, you will output like just the empty word. If it's relevant, you output relevant. And if it's not relevant, you output, let's say, irrelevant or erroneous or something like that. I noticed that when prompting LLMs to actually make decision, the more distant the classification word that you use in your decision, the more distant they are each other from each other in the embedding space, the better. There is less ambiguity for the LLM to answer. When if for example you have relevant and irrelevant, because the tokens are made of the same, the words are made of most of the same tokens, there could be an ambiguity in the decision capability in the decision, and it can make the system choose the wrong path. So actually, the wording of your decision is really important, and I think it's the same problem in many agentic systems. The more distance the words for your decision, the more distance they have with each other in the embedding space, the less tokens they have in common, the better will be the output.
Yep.
So here about decision system. Shit, my computer is completely dead. I wanted to show you also the Copilot, but unfortunately I don't have it here. So okay. I can, if you have if there is other questions, I can ask, and I will anyway. I will push the notebooks about the Copilot tonight, so people will be able to check it and to run it.
Okay.
Is there any question about, for example, here is a notebook about creating custom tools. So basically, what we do is we take the description of the function to create a tool. So it's kind of basic, but it allows people to add new tools to the system to satisfy their use case. So that's here is the graph that we use, and the system is able to, for example, to fetch the price of a cryptocurrency using the tool that we created, so the custom tool.
I see. So I don't see any other questions, but maybe we give it a few moments. But what I wanted to know is maybe we can explain, or you can explain what you wanted to show. I mean, it's unfortunate we cannot show it now, but on screen. But we can at least maybe we can talk a little bit about it, and you can say what the general concept or the idea is, and what it brings to the table. That helps people work with Neo4j and HybridAGI.
Sure. The copilot, for example, so the copilot is really about creating. So as you see, like when we create a graph program in Python, okay, but at the end, what you got is a program in Cypher, okay. So the copilot is actually a simple program that is used to ask the LLM to create this program, okay? And that's where the usefulness of having chosen a Cypher for the system helps, because the system is quite like large language model have been trained on many programming language and many language, and they are able to output a Cypher program. And basically, what for the system, we ask the system, for example, let's say you start with write a poem, okay? So the first step will be to convert this instruction, write a poem, into a plan. So this plan could be like a first step, I fetch some documents in memory to see if there is a poem about the given topic in memory. And then I write a draft. And after writing this draft, I ask the user if they're happy about the draft, and then I finish I give the last I give the last version of the poem, and then I finish the program. Okay. So the first step will be to like take this query from the user, convert it into a kind of natural language plan, which is going to be like a bullet list. And from this list, then you have a prompt that asks the LLM to format this plan into a program. So you give the LLM some examples on how it have to format the plan. And because each step is actually involving a lot of natural language and is just like changing the format, it doesn't have, the system doesn't have to learn or to, because actually LLM have not been trained on our DSL, okay? So they don't know the exact DSL. But if we give them the instruction to create it, like for example, we say, okay, for each action, you have to create a node that look like this, that have this ID, that have a purpose field, a tool field, a prompt field, what you have to do, put in the prompt, etc. Given that in the previous step you have given already all information, or you have created an intermediary steps that allow the system to populate these steps, the system is able to actually to create this program, this Cypher program. And so the whole idea, and that's why we created an interpreter and not a static language, because the goal at the end is to have, let's say you have an agent, but you cannot program it for all the tasks that it's going to perform, okay? And if we want to have a system that is general enough, we have to come up with a way to create new skills and new tasks on the go. And the way to do that is to actually use this Cypher intermediate language. And so the system is actually able to create on the go this representation, this Cypher program, for example, is able to create something similar and to save it into memory. So then if you ask again the system about the same task, it will be able to dynamically call the program that it just created. That's why HybridAGI have these features. So actually the dynamic call is needed if you want to have a program that is able to learn new tasks on the go. Okay, and so we have to. It's a way, because when you start your main program, let's say you start your main program, you just have your learning algorithms that say, okay, look for the programs in memory. If there is no program for the specific task, call create program, the subroutine create program, and then this subroutine create program is going to have some programs to actually come up with the actual Cypher program and save it into memory. Okay. The library, when you will look for known programs to solve a particular problems. Okay. At the beginning, the program memory will be almost empty. The only program that will be inside the memory will be your main program, and the program that your main program is calling using the program nodes. But as you use it, the library of tasks that the system will have will grow. Okay, it will grow over time. So actually, it was really important for us to have a way to embed the task, the programs, and to search for them in a dynamic way, in order to be able to when the library of program is growing in real time on the go, to have a way to fetch the correct one and execute it. So that's why we have these tools, like to search for known programs inside memory and to call them dynamically, and of course to add it into memory to save it.
Okay, cool. Yeah, that's really cool. It's a shame we cannot see it now in action, but maybe I don't know if you can record a video at some point and maybe add it to your
Yes,
to your GitHub page or something, where then people can follow up and see how it looks like on the other side. The only other question I see here is from Andrea, and that would bring us to the end anyway, from Andrea, and they ask, have you evaluated the models used in your repo and not used with text to Cypher? What are your results? I don't know if you played with that.
So text to Cypher is actually very different from what we do. Text to Cypher is used, like traditionally, Cypher is used to carry a knowledge graph. So if you look at text to Cypher, for example, I don't know if you already looked at this data set, but it's about carrying a knowledge graph. Here, we use what the goal of the system is to create a DSL based on Cypher, but it's not the graph program is not a traditional carry, I would say, that you use in Cypher, and it's really different. So here in this system, the Cypher language is used as a proxy, is used as a way to describe a graph in natural language, but it's not only about retrieving facts in a knowledge graph, which is two different things. So actually, it's very different from text to Cypher.
Okay, good. And maybe just to close it down, is what are your because we talked a little bit about this earlier, from large language models to local small language models, is what are your experiences here, and why have you chosen the tools you are working with now?
So first, there is a different, I would say, justification for our choice and design. First, I've been working on AI for I would say very long time, and the trend that we see on AI system is that when they always get better and smaller. Okay, it's something that I've been working with computer visions, and when we started using deep learning for computer visions, the system was quite big, and very quickly they reduced in size, and they got almost real-time frame rates, and they got better and better, and more importantly, smaller. So that's actually a global trend in ML, that as soon as there is a lot of money invested in machine learning, the size of the models is reducing and the capability is augmenting. So that's first justification. That's why we from the start we thought about if you have a system that requires multiple steps, the only way to reduce the cost of running the system is to actually perform computation on the client side. So actually on the computer users, and this can only be done with local LLMs. For example, let's say you have a system for predictions. Having the LLMs on the client is not really problematic. What is important is to have the graph database on the cloud, okay? So all your systems are going to be connected to Neo4j, to whatever the graph database you are using, okay? So actually, when you are using a neuro-symbolic system, the importance of the system shifts from the neural network to the data, to the structured data. So the graph database is really more important than the large language model. The large language model is used just as an execution engine, but the whole value is in the graph database. That's where you store your programs, your programs or plans. That's where you store your data, your business data, etc. So actually, when you're creating a program that is, for example, you have a team of workers and then they want to have a graph RAG, the thing that is going to be important to have on the cloud is the graph, not the LLM that you can run locally. And that way, you can actually reduce a lot the cost of running your systems.
Yeah, that's great. That's a good point. Very, very, very insightful view on this. And yeah, that's really, really good. Good that you made that connection here between using your own data is what makes the difference really, and your data should be in your graph database, and then from there exactly. you can use any LLM.
Exactly.
Really.
I think you mentioned it, but when all this craziness about LLMs started, not everybody was looking into graph database, but I think that a lot of professionals were actually looking into that because that was the way that they make like the data intensive systems are all based on the graph database, and graph database are really key for that. For example, I have some story when we started. For example, HybridAGI, we started with Redis graph, and they dropped the support for the graph database. And for me, I was like really surprised as someone from robotics, and I think many professionals was really also very surprised by that decision. And so they wanted to stick on a vector-only database. And for us, it was really something weird because graph database are really like the missing points, the missing link, I would say, in your architecture. They give the possibility to have insightful analysis, but also you can use them in many ways. Like for instance, in HybridAGI, we use a graph database in many ways that are not traditional, but it's because the graphs can describe almost everything. They can model almost everything, so you can actually use that to model many kind of algorithms, many kind of models, and not necessarily knowledge graphs, traditional knowledge graphs.
Yeah. Cool. Yeah, thank you very much. It's right. That was a good. I think that was a good end point to our session. Yeah, like I said, the links to the repository are in the video description on YouTube.
Yes, I will check my computer.
Yes,
I hope it's doing fine.
it's definitely out of our control this time. Mess. Yeah, no worries.
The effect. We talked about that, and like it's
yeah.
It's so it's so,
it happens. It happens.
yeah,
Don't worry
it's
about
up,
it. We
yeah,
can ever pick it up again at some point. So like I said earlier, next stream is tomorrow. We're going meta, but don't forget about the Neo4j developer survey. So
yeah.
that's currently running. So
And I
point.
will publish the notebook about the copilot on my LinkedIn. So
Okay, cool. And you can share that with me. Maybe then I can add it also
yeah,
to the video description.
obviously I will share it with you. And if people want to follow us on LinkedIn, I will be happy to connect with them.
Cool. Yeah. And I think with that, we're at the end of today's episode. Thank you very much, Yoan. Thank you, everybody, for watching. Like Yoan said, reach out to him and the team if you want to know more about HybridAGI. Check out the GitHub repo, give it a star, and play around with it some more. And let us know what you thought of this episode by giving it a thumbs up. That would be obviously great. And with that, have a good rest of your day. And
thank you, Alexander.
See you soon. Yeah, thank you, Yoan.
Thanks for Neo4j for having invited me, and thank everybody for participating in the chat.